Welcome back to my channel, and today I'll be continuing with the applications for integrals, this time with the length of curves. So, length of curves has its own formula, and you're talking about here the length of a smooth curve, so that's very important to remember. And it can be defined pretty much entirely by this formula right here. So you have the integral of something on the interval of a to b, and then the square root of 1 plus dy over dx squared dx. And this is if y is a smooth function of x. So if y is a smooth function of x. And you can do the same thing with the if you want to do x as a function of y. Again, you have an interval from a to b. You have 1 plus dx over dy squared this time, because you have x as a function of y, and it's just the same thing. So let's just let me just explain how this all comes about. So here's a it's just conceptually explaining what length of curves means. So you're trying to find the length of a curve over a certain distance. So here's just like a general x squared type graph, and you have the interval a to b here, and you want to find this length. You can quite easily actually estimate this length, right? Because you know delta x here, and you know delta y there. So you have, let me just draw it bigger, you have delta y and you have delta x. And using this, you can see that this is the hypotenuse here, which is approximately the length of that curve. And the hypotenuse here we can easily find. We know the hypotenuse is just the square root of x, the change in x plus the change in y, delta x, delta y squared. So basically we just take the change in x and the change in y, and we can find the hypotenuse. Now we can make this even more accurate, right? If we took the same curve, right, or any curve, and you made even smaller triangles along it to try to measure. So you had another triangle here, and this is delta x, or change in x, change in y, another triangle here, very small triangles, and you do the same thing, small triangle here, another small triangle, and you just keep adding these lengths here. So what in the end you get the sum of the square root of the change in x squared plus the change in y squared, right? But you can take this a step further even, and in the end I actually want to show you how it all really boils down to this, and it'll look very similar to that. We can take this a step further, and we say that Riemann sums are always written in the form of the integral of a function that is always a function of x, right, delta x. So what we can do to this right here, we can multiply the top and bottom by delta x. So just take delta x and top and bottom. And since this x squared is in a square root, if we simplify this, we actually get the sum of the square root of 1 plus delta y over delta x squared. So we just pretty much squared that, and we put it within the square root above. So actually let me just rewrite this, so it seems to be getting mushed together. We get the sum of delta x squared plus delta y squared over delta x, and oh sorry, one plus delta y over delta x. This one I meant to write like that. And this very much resembles this right here, because here, I'll just write this here. It is really just very closely this dy over dx squared dx. So you can very clearly, see where this is all coming from. So let's just start with let's just do one example today. Let's erase all of this. And here's our example. So if y is equal to 1/3 x squared plus 2 to the power of 3 over 2. This is our function, and I want to find the length of its curve from x is equal to 0 to x is equal to 3. So this is what I want to find. So basically, it's on the interval from 0 to 3. This is what 0 is a and 3 is b, respectively, right? So you can very clearly see already, we already have our a and b, so we already have our limits of the integral. But the first thing we need to do is find dy dx, because that is, we have this component and we have the 1, of course. So the only thing left to find is dy dx. So we can square it, and then we can take the integral of its square root. So let's do that. So dy dx of this, we're just again differentiating with respect to x, and we know our rules of differentiation, and we get 1/3, and this is actually a chain rule, right? You get 1/2 here, and then you get 3 over 2, and then times 2x. That's just chain rule. And this 3 and this 3 will cancel out, and this 2 and this 2 cancels out very simply. So then, if we write down what we have left, we just have this x left and x squared plus 2 to the power of 1/2. And if we simplify this further, we can write it as x square root of x squared plus 2. So that's our dy dx. And now we just put it back into this, and we already discussed that the interval of the limits of our integral are 0 and 3. And we have the square root of 1, again just following the formula, 1 plus dy dx squared dx. So 1 plus, now we have to add this dy dx squared, x square root of x squared plus 2 squared dx. So there we have it, and this actually represents the length of the curve. So now let's actually find this length by doing this integral. It's not as tedious as it may initially look, actually. So we continue on with this, and we simplify it, and we get 1 plus x squared plus 2 dx, which equals, let's write it here, equals square root of 1 plus x to the 4th plus 2x squared. You can just clearly see that this square root sign will very soon vanish, because this is just the square root of x squared plus 1 squared dx. So now we've already gotten rid of our square root, and we just have x squared plus 1 dx. And if we take the integral of this is very simple. We know our integrals rule, so it just becomes 1/3 x cubed plus x. And we have our limits set from 0 to 3, and we just plug in the numbers now. 3 cubed plus 3, and if we plug in 0, we get 0, so we're subtracting 0, and that gives us, in the end, this is 9 plus 3, and you get 12. So in the end, the length of the curve of this equation right here from 0 to 3 is just equal to 12. So thanks for watching. And that's it.